Okay, we are chapter 16, thermodynamics still. And last time we were looking at really Gibbs free energy. And that is delta G, and that is used again, basically free energy available to do some type of work. And we can use delta G to sort of figure out whether or not reactions are spontaneous or non-spontaneous, will sort of be product favored or reactant favored. If it is negative, it is typically a spontaneous process. If you end up with a positive delta G, it's going to be non-spontaneous. We've seen a couple of different sort of delta G formulas. The one we were kind of focused on a number of last time was this one here. This one has obviously our enthalpy and our entropy in here. And our entropy. And remember, again, as we talked about, you just got to be careful of units when using this one. Typically kilojoules for enthalpy, typically joules for entropy. So again, you have to do a conversion, otherwise you will find yourself off in terms of your answer. We also sort of use this one here to figure out a couple of things. For example, if a reaction is non-spontaneous, you can sort of rearrange this equation and solve for T by setting delta G equal to 0. And when you do that, T would equal delta H divided by delta S, which gives you an opportunity to maybe figure out what temperature a reaction could become spontaneous, if it's possible. If it was a non-spontaneous reaction. We also saw that we have the entropy of phase changes. So, we have the entropy of fusion, we have the entropy of vaporization. That also can be solved basically by this equation. In this case, you would be solving for delta S, which would give you delta H divided by T here. Remember that this one does look very much like the delta S of the surroundings, except it does not have the negative in it. Again, the negative in the delta S of the surroundings is for that opposite relationship of enthalpy and the change that occurs in the surroundings. So we could use this for phase changes. The delta H here would typically be either, for example, delta H of fusion, which is that energy needed to go from solid to liquid or backwards. Could also be the delta H of vaporization, which is that energy needed to do this transition of going from liquid to gas or gas back to liquid. The only thing really that will change depending on sort of which direction you're going is really the sign of that delta H. Again, if it's an endothermic process, like you're going from solid to liquid, you'll end up with a positive value for entropy. And that makes sense because if you're going from solid to liquid, you're obviously going to more disorder in the liquid state than you had in the solid state. And you would expect the delta S to be a positive number. And vice versa, if you were going, say, from gas back to liquid, that's an exothermic process, condensation, and your delta H in that case would actually be a negative value, which would lead to a negative delta S, which once again would also make sense as you're going from gas molecules flying around to more organized liquid molecules. And obviously you're creating a lot more order, and we would expect our delta S value to be negative. So again, those signs should sort of agree depending on which way you are going. Any questions on any of that stuff there? And I think we also talked about last time, but just a reminder that if you are doing something like this type of calculation, say for the vaporization, stuff like that, remember that if you're not using water, it will have different values. And obviously the delta H of vaporization for water and also different boiling points and melting points as well as if it's a different substance. So just want to make sure you don't lock in always with water sort of values. All right, so it's been a little bit since we talked about the equilibrium constant, so I feel like we don't want to forget about our friend K here. So let's talk a little bit about Gibbs free energy and the equilibrium constant. So here we have an equation which is delta G is equal to delta G naught plus RT natural log of Q. And thank you. This equation here It's basically for sort of non-standard conditions. So if you take a look at this, you could think of this as the delta G under sort of non-standard conditions. Remember that standard conditions basically means that if you're dealing with pressures, everybody's going to be 1 atmosphere or 1 bar, basically. So if you're dealing with any type of pressure, they should be 1 atmosphere. If you're dealing with any type of concentration, they should also be 1 molar. So those are kind of the hallmarks of sort of a standard condition. And usually, if you look up sort of like thermodynamic values and tables, those are sort of the characteristics or properties at which those numbers come from. This is sort of our delta G under standard condition. Again, that's sort of what the little knot sort of represents. Um, this is the gas constant, but it is the one obviously here that involves energy. So it's that 8.314 version of it. T is our temperature in Kelvin. And Q is our reaction quotient, and that is, again, the same one that we've seen previously, calculated the exact same way as you do K. So that's going to be your products over your reactants, obviously taking any coefficients into account as well. So if you have some type of situation where maybe you're not under these standard conditions, you could see the effect on the delta G of a reaction. And again, probably it's going to be something about pressure difference than 1 or concentrations that are not 1. So those are sort of what you want to look at. Yeah. 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 Are you talking about these? Yeah, those two. Yeah. So these two is this is basically your delta G under sort of non-standard conditions. So again, like I said, it's something to do with maybe the pressures aren't all 1 atmosphere, the concentration aren't 1 molar. This delta G would in most cases be your delta G that you would go to the table and do your delta G of your products minus your delta G of your reactants. If it wasn't given to you, you'd most likely that is how you would calculate that delta G. And that would be then under standard conditions. So that one there would be under standard conditions. You're going to kind of a lot of times calculate probably the delta G as a result of it not being under standard conditions. Other questions? Okay. So this is again, as I talked about, we've seen a number of sort of formulas with delta G, and again, you kind of want to pick the right one to use in sort of the right situation, sort of the best piece of advice. So obviously here, if you're given some type of concentrations, pressures that are probably not standard, then this is probably the one you should look at. And like I said, sometimes they may actually give you the delta G not in the problem, or sometimes you just need to go and calculate it yourself from the table. So it varies. When we do get to equilibrium, delta G will equal 0, and Q will actually be the equilibrium constant, which if we substitute that into this top equation, will give us the other equation here, which is the delta G naught is equal to minus RT natural log of K. These are our kind of normal guys here. This is going to be obviously our free energy. That's our gas constant. That's our temperature in Kelvin. And that, of course, is our equilibrium constant. So we have, these, we have, this one here that we saw a second ago. So, and we also have obviously this one here as well. So there's a few different sort of formulas that involve delta G. So again, just to summarize, probably the best approach would be if you were asked to calculate delta G and pretty much all you're given is like an equation, I would roll with this one. Just go to the table, do products minus reactants. If you're given like some delta H's or delta S's, then obviously this would be the right one to do. Or maybe you're asked to calculate delta H or delta S first, and then you could go into that equation and do it. Obviously, anything having to do with an equilibrium constant, you should top down to the bottom here. And then non-standard conditions, that is what you should do there. So you really kind of want to think about sort of what's going on in the problem and sort of pick the right sort of formula that will work with it. Questions on that there. All right, so obviously here, if we take a little closer look at the delta G, one with our equilibrium constant, the good news is this is an equilibrium constant, which we hopefully should know something about at this point in the class. And that means that as long as you understand sort of the equilibrium constant, you probably can figure out the rest of this. If we have a large value of K, that should mean that we should mainly have products when we reach equilibrium. The only way to sort of reach products is it needs to be spontaneous and head towards the product side, which means we should probably have a negative delta G, which would mean that reaction would be spontaneous and head towards the product side. Now, if we have a small K value, that would mean, like normal, that we mainly have reactants when we reach equilibrium. And if we mainly have reactants, we're really not heading to the product side. We're kind of hanging out over there on the reactant side. And that would probably correlate to a positive value for delta G. And obviously here, if K equals 0, then we will end up with basically a equal amount of reactants. Our products are sort of favored in that case. All right, so let's try some here. Delta G of O2 is 0 kilojoules. All right, calculate the equilibrium constant here for this following reaction. Okay, let's take a look. So obviously we're looking for an equilibrium constant, so that should narrow down the search of which formula to use. We'll use the one that has the equilibrium constant in it. So we're looking to solve for the equilibrium constant. In this case, our temperature, we got to convert to Kelvin, so that's going to give us a 298. Obviously, R is a constant, 8.314 joules per Kelvin per mole. Here we do actually need to calculate the delta G, and once again, that would be under standard conditions. So we'll go to table and find our values. We're going to do basically our products minus our reactants. And in this case, our product is O2, so that's going to be 3 times 0 kilojoules, minus our reactants, which is 2 times 163.4. And that's going to give us a delta H here of negative 326.8 kilojoules here. So I now have this, and this. So I think we have everything we need here to solve. I'm going to put it in here. So we can go negative 326.8. I am going to multiply it by 1,000 to turn it into joules. The reason I'm doing that, so I don't get any unit problems over here with R, which is in joules and not kilojoules. So we don't have any problems on the road here. So that's going to be minus 8.314 joules per Kelvin per mole. We're going to go with our 298 there and our natural log of K. So now I don't really have to worry about it since these are both in joules. Obviously, you could also convert your R to kilojoules if you want to do that as well. So we're going to take basically all this stuff and divide it to the other side. And that's going to give us divided by 8.314 and divided by a 298. Maybe hit the right number there. That'd be good too. Let's try that one more time here. Whoops. All right, third time's the charm. Maybe the fourth time's the charm here. Let's try that. There we go. All right, 8.314 and a 298. There we go. That's going to give us a positive here. 131.9 is equal to the natural log of K. Obviously, negative and negative is going to turn that back into a positive. We're going to E both sides here. And that will just make that K. And that's going to get us here an equilibrium constant of, looks like maybe 1.9 times 10 to the 57 in this case here. Again, depending on rounding, you might get a slightly different number if you round a little bit before you did the E of both sides and all that kind of stuff. Any questions on that one there? A couple of things does agree, right? We had a negative value here for delta G, which would indicate that this reaction is probably spontaneous, should be heading to the product side in this case. And that would mean that we should end up with a large value of K, which definitely that would qualify as large, I would imagine. Yeah. Any questions on that there? So again, these numbers should agree with each other. For example, again, if you got a positive G here, you probably should not have a large value of K, right? So you have a more small value of K when you do that. All right, let's take a look at another one here. Calculate the delta G naught for this reaction here. If the KSP is 1.7 times 10 to the minus. Okay, so on this one again, we do have a KSP, which is still a K value. So, and we're looking for delta G. So once again, we're going to go with the same formula there that has the K in it. And in this case, we have pretty much everything we need on this side. Obviously, like normal here, got to do a little conversion there, some temperature. And other than that, I think we're good. So we'll go delta G naught is equal to minus 8.314 joules per Kelvin per mole, which is our R value, our temperature being 298. Natural log of our KSP here, 1.7 times 10 to minus 6. I'll do this way, I guess. 8, 1.7 minus 6. So that is going to get me here. It looks like 32914. I think these are joules, are approximately 33 kilojoules, I suppose, if kind of convert it back into kilojoules in this case. Not any question on that there. Yeah. Yeah, so K is just an equilibrium constant. Doesn't matter what the little subscript is, they're all the same. So they're all basically considered equilibrium constants. Yep. Kind of similar to what we did in that one chapter where we kind of added like the KSP. We added that to like a KF type of equation. So it doesn't really matter. They're all the same. Again, in terms of agreement here, we definitely have a small K value, and that gives us a positive delta G, which means probably non-spontaneous reactants favored. And that all kind of, again, agrees with each other. All right. One last example here, I think. Delta G naught for the following reaction is 2.6 kilojoules per mole at 25 degrees. In one experiment, the initial pressure of H2 was 4.26, I2 0.024, and HI 0.23. What is the delta G for this reaction, and which way will this reaction go? Will it be products? Okay, let's take a look at this one. So the first thing you should hopefully notice is we are given some pressures, and these pressures are not all one atmosphere, and that tells us this is sort of like non-standard conditions here, and that should then direct you to obviously our delta G equation that has that in it, and RT natural log of Q. By the way, this is plus, and people always want to put a minus there and subtract that one. So in this case, they were nice enough to give us the delta G naught. So if not, obviously you would have to go to the table and calculate it yourself. Products minus reactants. We obviously have R, which is our 8.314, and our temperature here of 298. So we do need to kind of calculate Q here, and Q again is the reaction quotient. So that would be in this case, really not really the concentration here. It'd be more the pressure. Again there. So this would be the partial pressure squared of HI divided by the partial pressure there of H2 and the partial pressure of I2. So put in our numbers here, we got 0.23 squared divided by 4.26 and 0.024. That's going to give us a Q value here of 0.23 squared divided by 4.26 and 0.024. Gives us a Q value of 0.5174. Now I think we got everything that we need, so we can put it in. So our delta G here, gonna be our delta G naught. Once again, just being mindful of units, I am going to multiply this number by 1,000 to get me into joules again, because my R is in joules as well. So again, you could go kilojoules if you prefer. Plus my R and my temperature here, 298, natural log of 0.5174. So if we kind of clean up the right-hand side there, let's see, we'll take the natural log of this guy and we'll times it by 298 and then times it by 8.314. That looks like we're going to end up with minus 1632.5. And then obviously here in the front end of it, we got about 2600 joules here, right? So at this point, we will end up with that minus, actually that plus that. And that's going to give me something like 967 joules in this case, or if you want to kind of put it into kilojoules, which is typically what we kind of see here, that'd be 0.967 kilojoules in this case. First off, any question on the calculation? Now, we do see here we ended up with a delta G that's positive, and that should tell us that really this reaction is sort of not favoring the products, but is favoring the reactants. So this should favor the reactants in this case, as it's sort of non-spontaneous. Any questions on that there? Yeah. Not necessarily. You could, depending on. So this also allows you, for example, like you can play with perhaps pressures or concentrations and perhaps turn it into a spontaneous reaction. So it just sort of depends on the reaction and the conditions, stuff like that. So not necessarily that you always end up with a positive one. Other questions? Because remember, for example, in this situation here, under standard conditions, this reaction also is reactive favor. So this didn't do much to move it in the other direction in that sense, right? So you would have to sort of do a little switch around in terms of your pressures and maybe try to get it in that direction. Other questions? All right, that should be this chapter. Sounds good. There's thermodynamics. Okay, so the next place we're going is chapter 17. We're talking about electrochemistry in this chapter. And the main part of this chapter is about galvanic cells and some other stuff. But just to make sure everybody is sort of on the same page, we're going to kind of review, which may be review for some of you, or maybe not, depending on whoever you had for Chem 50, I suppose. But we're going to talk about redox reactions in general, how to balance redox reactions, oxidation states, and that type of stuff. So if this is something you already know, I apologize, but to just make sure everybody's on the same page, hopefully it'll be helpful for everybody. And then we'll get into really kind of the heart of the chapter at that point. So when we talk about electrochemical sort of processes, it's really the idea of an oxidation reduction reactions, which are sometimes referred to as redox reactions. And redox reactions basically is a process where we can use electrons that are released to go out and do some type of work. For example, like a battery, sort of in that situation, you can kind of use that to convert it to electricity. So when we talk about redox sort of reactions in general, actually, it's just back a page here. When we talk about redox reactions, there is the oxidation, which once again means the loss of electrons. Reduction means that you gain electrons. And again, sometimes people remember this as Leo the lion goes grr, so loss of electrons, oxidation, gain of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. So these are two very common sort of definitions of oxidation and reduction, which we deal with a lot here in general chemistry. If you continue on to organic, you will look more at the other sort of definition of oxidation reduction, which is you gain oxygen as you go from reactants to products, is another sort of oxidation definition. And also you lose hydrogen as you go from reactants to products. And the opposite is true for reduction. You lose oxygen as you go from reactants to products. or you gain hydrogen as you go from reactants to products. Again, in here, probably not going to see too much of those definitions, but when you go to organic, that's usually all you sort of look at because it deals a lot with all nonmetals. So we just look at sort of, it's much easier to look at oxygen or hydrogen either being gained or lose in that situation. Now, both of these things always happen together, which means if somebody gets oxidized, somebody else gets reduced. So it always happens at the same time. And obviously, if you get oxidized, your oxidation state changes, and really you become more positive because you lost electrons. Now you have more protons than electrons. So you're going to be more positive than you started with. And if you gain electrons through reduction, you're now going to be more negative than you started with because you gain more negative electrons. So really an easy way to sort of figure out, for example, if something is being oxidized or reduced is if you're not sure, you can just use a basic number line. And there's usually positive numbers to the right of zero, negative numbers to the left of zero. And if you look at the oxidation state, which we'll talk about shortly here, of one element on the reactant side to the product side, and you see that it is moving in this direction, the positive direction, then that thing is going through oxidation. If you look at the oxidation states or numbers from reactants to products and the thing is getting more negative or heading towards the negative direction, that means that that substance is going through reduction. So it's just a really easy sort of way to figure it out if you're not sure. So for example, if we had iron with a +3 that went to iron with a +2, we can just pop it up there on the number line and go, okay, this guy obviously is +3, this one's +2, +3 is over here, and it ends at +2, which would be moving in this direction towards the negative side. So this guy is going through reduction. And one of the nice things about figuring out one of them is the opposite thing is happening to the other thing that's there. So you, in a sense, only need to figure out really one thing who's being oxidized, who's being reduced, and you can just, the opposite thing should be happening to the other part there. Question up there. All right, so as I mentioned before, we do use these sort of oxidation and reduction reactions to do some type of work. So if we take a look at low magnesium oxide formation, the oxidation state of magnesium here is 0 because it's in this natural uncombined state. That's pretty much everybody. Same thing with oxygen. That's naturally how oxygen comes as a 2. When these two guys come together, we do get a ionic compound that's formed, and that magnesium is group 2 has a +2, and that is oxygen, which is a -2. So once again, if you're not sure, you can very simply just put it on the number line there. So if we look at magnesium on the left, it is starting at 0, and on the right, it is ending at +2. That is moving in the positive direction. So our magnesium here is going through oxidation. By default, I know automatically then that the oxygen here is going through reduction. I could also do it for oxygen. It starts at 0 and ends on the right-hand side at -2, so it's becoming more negative and going through reduction. So super easy way to sort of figure that out. By the way, I should also know that that should be the case because this is an ionic compound. And when an ionic compound is formed, it's always the metal that gives away the electrons, right? So it always loses the electrons. The nonmetal is always the one that accepts it. So in an ionic compound, it's pretty easy to figure out who's being oxidized, who's being reduced, because it should always be the metal being oxidized, giving away the electrons. The nonmetal should always be picking up those electrons and being reduced. We could take this reaction and split it up into what is known as half reactions. And these are half reactions here. And there's an oxidation half reaction and a reduction half reaction. And they basically show half of what's going on. So when we look at magnesium here going from 0 to +2, it is going to give off 4 electrons here. And we know this is the oxidation half reaction because the electrons in that half reaction are on the product side. So if you see a half reaction where electrons are written on the product side, you should know that that is an oxidation. The idea there it is like is being given off. Why is it 4 electrons here? Because each magnesium gives away 2, becomes positive 2, and there's 2 magnesium, so that's 4 electrons basically. So that's where the 4 electrons come from. Oxygen over here is the reduction half reaction, and it is going to gain those 4 electrons, and that is how you know this is the reduction half reaction. The electron should be a reactant. So if you see electrons on the reactant side, then you know that that is a reduction, like they're being gained. Same idea here. We basically have 2 oxygens. Each oxygen is going to pick up 2 electrons, and that will take up the 4 electrons that are coming in this case. Once again, if you took this reaction and just added it back together in a simple redox reaction, when you add the half reactions together, you always want to make sure that the electrons are the same number on each side of the arrow, and they should also cancel out. So whatever's on the left-hand side and right-hand side should cancel or reduce, and for sure electrons should always cancel out. Now, when you write half reactions, you may not always have the equal number of electrons in each half reaction. So sometimes before you add those half reactions back together, you do need to multiply either one half reaction or both half reactions by a common number to get the electrons to be the same. But that's always something when you put them together, electrons should always completely transfer out or cancel out. And the idea there is whatever electrons is being lost by who's being oxidized should be the exact same number of electrons that are gained by whoever's basically being reduced and gaining those electrons. There should be a nice perfect transfer happening there. And again, that's what we see here, our half reactions adding back together, combining those, and these 2 ions will come together to make our ionic compound here. We take a look at another example here, calcium oxide. This is 0, this is 0. This is going to be +2 and -2. So once again, if we take a look at it, our calcium starting at 0, ending at +2, should be oxidized as we should expect. Our oxygen here should be reduced. And again, the oxygen starting at 0, ending at -2 in this case, and it is being reduced. This again is an ionic compound. And as you probably remember, redox reactions are the big classification of reactions that are more specifically called synthesis reactions, fall under that category, decomposition reactions, single replacement reactions, and combustion reactions. These are all specific ways to classify a redox reaction. This obviously would be a synthesis or a combustion reaction, actually. Example. So once again here, our metal being oxidized, basically sending its electrons over to our oxygen in this particular case, where it's going to be accepted. And that is, again, where they basically form charges in this case, right? Now, another couple of things that are sometimes asked is oxidizing agents and reducing agents. And oxidizing agents and reducing agents is a different question than what is being oxidized and what is being reduced. So the oxidizing agent is the substance that gets reduced, while the reducing agent, as it says there, is the substance that gets oxidized. So why are they calling it? Why are they called that? The oxidizing agent is a substance that gets reduced. So that means in order for him to gain electrons, he has to cause somebody else to lose electrons. So he's causing somebody else to be oxidized, and that is why it is known as the oxidizing agent. The reducing agent is sort of the same explanation. In order for when it gets oxidized, it's going to release electrons. And by that process, it's going to cause somebody else to get reduced. So once again, if you're asked what is being oxidized and what is being reduced, that is a different question than what is the oxidizing agent and what is the reducing agent. And the previous example, calcium was oxidized, so that would be our reducing agent. Oxygen was reduced, and that would be our oxidizing agent in this case. By the way, all of those things are found on this side of the arrow, the reactant side. Your things being oxidized, your things being reduced, your oxidizing agent, your reducing agent, all those things are found on the reactant side of the arrow. Questions on that there? So as I mentioned before, there's a couple other definitions of oxidation and reduction. And like I said, we're not going to probably see too much of it in here. But as I mentioned, you can gain oxygen from reactants to products or lose hydrogen from reactants to products. Then reduction is the opposite definitions there. Lose oxygen from reactants to products and gain hydrogen reactants to products. So if we take a look at this, we could clearly see, for example, here, the tin has some oxygen on the left, not so much oxygen there on the right. So it is being reduced. The carbon here has no oxygen on the left and gains some oxygen there on the right, which means it is oxidized. Yeah. And because the carbon here is oxidized, the carbon would be our reducing agent. Because the tin here is being reduced, this would be our oxidizing agent in this particular case. Now, in this particular case, you could still look at the tin because you do have a metal here. And you can see if you looked at the tin on the left-hand side, that's a +4. And if you look at the tin on the right-hand side, that is a 0. So once again, if you pop that onto the number line, starting at +4, ending at 0, becoming more negative, and it is going to be reduced in this case. So again, in this case, you happen to have a metal that would allow you to maybe figure it out a little bit easier. But again, we probably won't deal too much with the oxygen and hydrogen, but you definitely will when you go off to organic. Now, speaking of that, in order to be able to really analyze sort of what is going on, we do have to know what the oxidation number of everybody is, also sometimes referred to as the oxidation state. And the oxidation number or state is the charge that the atom would have if all the electrons were completely sort of transferred. And there are some rules, some of which we talked about previously here. Pretty much the first rule is if you have any element by itself, it's not combined with anybody else, it will have an oxidation state of 0. So anybody just kind of naturally how they come, not combined, going to be an oxidation state of 0. If you have a monoatomic ion, then the oxidation number is equal to this ion. So lithium would be +1, iron 3 would have a +3 oxidation state. Oxygen, which is usually a really good place to start, would have a -2. By the way, when you do write oxidation numbers or states, you should include the pluses and the minuses with it, and not just the number. Yeah, so if it's +3, write +3. Don't just write 3. If it's -3, obviously -3 as well. Now, the oxidation of oxygen, like I said, is usually a really good place to start with in terms of identifying oxidation states. It is typically -2. The only time it's not -2 is if it's actually peroxide, and that's a polyatomic ion here, which is O22 minus. It will have a -1 oxidation state, like we see here in hydrogen peroxide. That's actually -1, and that is +1 in that situation. So how do you know if it is sort of oxygen versus peroxide? Usually that 2 hangs around on the bottom, so you'll usually see it, like you kind of see it over here. You had like sodium peroxide, you would have maybe something like this as well, and you'll kind of see the extra 2 sort of hanging out on the bottom and stuff like that. I would say probably 99% of the time it's probably safe to just you see an oxygen, probably assume that it is going to most likely be oxygen, and but it could be peroxide in special cases. The oxidation state of hydrogen is +1 unless hydrogen comes after a metal, in which it's hydride, which means it would be -1. Like if you had lithium hydride here, that would be +1, -1 situation. Group 1 metals are +1. Group 2 are +2. Fluorine is always -1. When you do add up all the oxidation numbers, they do need to equal the overall charge on that ion, or obviously if it's neutral, it needs to add up to 0. So that's obviously an option. So if we take a look at our friend bicarbonate here, I would say usually a pretty good approach is if you got kind of like a 3-pack of elements there, I would go right, left, and save the element in the middle for the end in terms of assigning numbers. So here we would have oxygen, which is -2. There are 3 of them, which kind of gives us an overall -6 happening for the oxygens. Going to the left-hand side there, that's hydrogen, which is +1. Now, in this particular case, the bicarbonate does equal -1, which means when you add up all of your oxidation numbers, it doesn't equal -1, which means in this case, I believe, if my math is not too bad there, +4 would be a winner for the carbon. +1 +4 is +5, -6 is -1 overall. So just to be clear, the oxidation state of hydrogen +1 is how you should write it. The oxidation state of carbon is +4, and the oxidation state of oxygen is -2. It is not -6. Yeah. So when you're asked for the oxidation state, it's not like the grand total of all of them there. It is one individual one, so you should not do something like -6 for oxygen. In this case, it should just be -2. Any questions on that there? All right, so why don't you give it a go here for these, for each of them. So we'll start here. That's oxygen, which should be -2. And obviously that's lithium, which should be its normal +1 since it's group 1. So our oxygen there, -2 on our lithium is +1. Coming over here, we have fluorine, which is -1, and there's 3 of them, gives you -3. Overall, this is neutral, should equal 0. That means the phosphorus here is going with a +3 in this particular case. A reminder that when we talk about oxidation numbers, they're not always going to be the same sort of charge that you think about when you think about sort of ionic compounds and ions. And that is because in this situation, they are not transferring electrons, but they're sharing electrons. So things that we normally, for example, associate with like a negative charge in an ionic compound, because it is receiving all those electrons, uh, be, can be more positive depending on what it is actually sharing electrons with. And if you think about just this situation here, they are sharing electrons here. Definitely fluorine is more electronegative than phosphorus, which means each of those fluorine bonds is going to suck the electrons towards the fluorine, and that's going to make our phosphorus more and more positive in this case. Again, because they're sharing electrons here. It's not like a situation where the phosphorus is receiving the electrons from a metal where it become negative. We take a look here at our nitric acid here. That's going to be a -2, and that's going to give us a -6 overall. It is neutral. Going to the other side, hydrogen is going to be +1. That means in this situation here, it looks like it's going to be a +5 to get us to 0. So hydrogen would be +1. Nitrogen here would be +5, and oxygen would be -2. Again, we normally think about nitrogen as maybe being -3 in an ionic compound when it's receiving those electrons. But once again here, just roughly draw it, not correctly, obviously, with all the proper bonds. In this case, nitrogen is less electronegative than the oxygen. So again, electrons are going to head this way, causing this guy to become more positive in this situation because they're sharing electrons, not transferring electrons in this case. Lastly, here we take a look over at dichromate. That's going to be a -2. And that's going to be us a -14. In this case, we do need to end up at -2 overall. We don't have just one chromium here, but we actually have two. Do a little math problem if you like. But I believe in this case, we're looking at a +6 6 would perhaps do it. That would give us a plus 12 minus 14 equals minus 2. That seems good. And that means here our chromium would be plus 6. Our oxygen here would be minus 2. Any questions on how to assign oxidation states? Really, really important in this chapter to understand, are you looking at something being oxidized? Are you looking at something being reduced? It's very important for calculations as well to know what calculation you should do and where you should put the numbers. Any questions on that there? Okay. So the next thing we're going to talk about actually is how to balance a little bit more complicated redox reactions. So again, if you have a basic redox reaction, just two half reactions, you really just need to make sure the electrons have the same number, add them back together, cancel out the electrons. Now, if we were wanting to balance a redox reaction in acidic solutions, our basic solutions, it's a little bit of a different process. So let's just go through this process here, just to again make sure everybody's on the same page as to how to do this. The first thing you would want to do perhaps is just kind of figure out what is going on in terms of who's being oxidized, who's being reduced. So if I start assigning some oxidation numbers here, my iron obviously is plus 2. We just did this one on the previous page there, so that was plus 6. That was minus 2. And obviously here are plus 3 and our plus 3 happening. So again, if we look at the iron to start with here, the iron is starting at plus 2 on the left-hand side, and it is ending at plus 3 on the right-hand side. It is becoming more positive. That means my iron here is being oxidized. The chromium here is starting at plus 6. Let's go over here. And it's ending at plus 3, which means it's moving in the negative direction. It is the chromium here that is being reduced. That would also mean that the iron 2 here is my reducing agent. The dichromate here, or the chromium, is my oxidizing agent. Any questions on any of that part there? All right, so the first step after sort of having a good idea of what everything is and what's going on is you want to take the reaction and split it up into the two half reactions. Very simple way to do that is just find the same elements and put them together. So I have an iron on the left and I see an iron on the right. So those two should go together in half reaction. I see a chromium on the left and a chromium on the right. So those two should basically go together. We also know now that, again, our iron here is our oxidizing half reaction. This is our reduction half reaction that we just figured out. All right, so that's the first thing, is basically split into half reactions. Then you want to balance all elements except hydrogen and oxygen. So we're just going to balance all the elements like we're balancing an equation with coefficients. We're going to balance all the elements except hydrogen and oxygen. So in the case of the first half reaction, there's just one iron on each side. We're good. They have different charges, but there's just one iron. There's two chromiums on the left and only one on the right. So we do need to put a 2 over there on the right-hand side, again, to balance it. Now that we've balanced all the other elements, it is time to balance oxygen. And the way we balance oxygen in this method is we use water to balance oxygen. So we use water to balance the oxygens. The problem, though, with using water to balance the oxygens is you're not just adding oxygen, but you're also adding hydrogen. So every time you add a water, you're actually putting extra hydrogens on one side. So we use water on one side, then 2H pluses on the opposite side. And those 2H pluses are to take care of the extra hydrogens we added for the water. When this is all said and done, this equation does need to be balanced basically two ways. It has to be balanced like a normal equation, same number of elements on each side. It also has to be balanced in terms of charge on each side. It has to be the same charge on each side of the arrow. So with that in mind, there's obviously no oxygen happening there in the top equation. The bottom equation has some oxygen. So this has 7 oxygens on the left, none on the right. So I'm going to put 7 waters on the right-hand side. Because I put those 7 waters to balance everything out, I will have to put 14 hydrogens on the left-hand side here to balance it out. At this point, we are ready to add electrons, and we're going to add electrons to balance out the charge on each side. Now, the charges on each side do not need to equal 0. They just need to be the same number on each side. You need to add the negatively charged electrons to whichever side needs it. Best and easiest way to do it is just take overall charges of everything. You shouldn't go element by element because the overall oxidation number does that for you. So why do it individually? So this is +2 overall on this side. This is +3 overall on this side. That means I need an electron on that side, which would give me +3, and -1 gives me a +2 on the right to match the +2 on the left. If I take a look over here on the bottom one, that's a +14. This entire thing's a -2. That's a grand total of +12 on the left. This is 2 times 3 is +6, and that is 0. That's a +6 on the right. So this guy would need 6 electrons on the left-hand side, which would give me -6. -6 and +12 will give me a +6 on the left and a +6 on the right. First off, any questions on that there? So I also know that perhaps I did this correctly because I know that the top reaction is the oxidation reaction, which means electrons should end up on the product side, which is good. The bottom one is the reduction half reaction, which means electrons should end up on the reactant side, which is also good. You should never add electrons to the same side because you screwed up definitely in that case. Yeah. So this is also why it's good to take a moment at the beginning and just try to figure out, who's being oxidized and who's being reduced so that when you get to this step, if you did add it to the correct side or not. Any questions on that there? All right, I'm just going to kind of clean up some of the extra scribble here so I can continue on this page here, I think. Maybe get rid of those guys here and that. All right, now that we did it, we're almost ready to add these back together. A reminder, as we talked about before, basically before we could add these half reactions back together, the number of electrons in each half reaction does need to be the same, and in this case, they are not. Top one has 1 electron, bottom one has 6. So we do need to multiply the top half reaction by 6 to get us the same number of electrons. So I'm just going to write it underneath here. So that will give me 6 irons goes to 6 iron 3s and 6 electrons. Now that we have everybody with the same number of electrons, we could add these back together. So now we could add, as long as we got the same number of electrons in each, you could add the 2 half reactions together. All right, should always happen is electrons should always cancel out. In this case, that looks like everything. So everybody on the left stays on the left of the arrow, everybody on the right stays on the right. So we will end up with 14 H pluses plus a dichromate plus 6 iron 2s. Goes to the right-hand side of the arrow, 2 chromiums, 7 waters, and 6 of the iron 3. So if I did not screw this up, this should be balanced in acidic conditions. So how do I know if it's balanced? Well, first off, it needs to be like a normal equation. I got 14 hydrogens there, 14 there, so that's good. 2 CRs, 2 CRs, 7 oxygens, 7 oxygens, 6 irons, 6 irons. So that is balanced like a normal equation. This gives me plus 14 plus, -2 and plus 12. So that gives me a lot there to count there. That's 26, 24 a net. positive 24 on the left. Over here on the right, we got plus 6, we got 0, and we got plus 18. 18 and 6 is plus 24 on the right. So we are balanced in acidic and conditions in this case. First off, any questions on that there? Now, if we wanted basic conditions, there are a couple ways you could do it, but to be honest with you, the easiest way to do it is basically just to do what we just did, which is just do it in acidic conditions. And at the end, you could then just turn it into basic conditions. So that's probably the easiest move. And maybe I'll go up here with it so I could just show you what we need to do. Let's get rid of some of this here. A middle spot here just to show. All right. So the easiest way to kind of do basic, like I said, is kind of like at the end, after you do acidic, you could turn it into basic. So if I take my equation from the bottom there, I got 14 H pluses plus Cr2O72 minus plus my 6 Fe2 plus goes to 2 Cr3 plus 7 waters and 6 iron threes. So now I want to turn this guy into basic. So to turn it into basic, we actually add OH minus to both sides. So we're going to add some hydroxide to both sides. The amount of hydroxide that we add is going to be equal to the amount of H pluses. So in this particular case, we have 14 H pluses. That means we would add 14 OH minuses to the left-hand side. We would also add 14 OH minuses to the right-hand side. So you add OH minus, that's equal to the number of H pluses you have. Now on the side where I have H plus and OH minus, those two guys will come together to make 14 waters. And usually at this point, you could reduce down some waters. You got 7 on this side. Will then leave you a net of 7 waters on the left. Everything else pretty much going to be the same here. So we'll just recopy it here, going this way. Obviously, my water is gone on the right-hand side because I cancel it out. And I have 14 OH minuses. And now I should be balanced in basic conditions. And it should still be balanced the same way. 14 hydrogens on each side, 2 chromiums on each side, 7 oxygens plus 7 more is 14, gives me 14 on that side, 6 irons. Overall charge, that's going to be 0. That's going to be minus 2. That's going to be plus 12. That is a plus 10 on the left. That is a plus 6. That is a plus 18. And that is a minus 14. And that's going to give us basically a plus 4 and a plus 6 gives us a plus 10. So we're balanced again both ways, like a normal equation, and the charge on each side is balanced. Any questions on that there? By the way, how do I also know I'm balanced in basic conditions? Because I kind of see hydroxide in my equation, so that's kind of good. By the way, I know I'm balanced in acidic conditions down here because I see H plus in my equation as well. Yeah, so that's how that should work as well. Any questions on those steps there? All right, we will lay it up there for today.